All right, so let's continue our afternoon meeting. It's a great pleasure to introduce Rodolfo Aguilar from CIMAT, who's going to tell us about infinitesimal methods and Clemens Conjecture.
Thank you. Thank you so much for the invitation. It's my pleasure to be here and seeing so many friends, and I'm especially happy about this audience for this talk. So I don't have a memory dispenser or a story, but I can tell the story how I learned the theory about collider Spencer or infinitesimal methods, and this was in collaboration with Green and Griffiths. So the story is as follows. Philip was giving a talk in Bulgaria, in Sunny Beach, about field maps of canonical pairs. So we were in the audience with another postdoc here, and we were saying, like, we should make a reading seminar about the Friedman paper on anti-canonical pairs for surfaces. So we did. We started a seminar, a reading group here, and Philip used to come from time to time. So he was pointing some reference, he was explaining something to us, and we were discussing some questions. So Friedman paper is about surfaces mostly or entirely. And so the first question was, what can we do in dimension 3? So that's the first part of the talk. I'm going to try to tell you what we did on this dimension 3, following those kind of ideas. And then I'm going to talk about some work that I did by myself, inspired pretty much by this work with them. And actually, I should call the talk Infinitesimal Methods in Mixed Hodge Theory, Mixed Hodge Structures. But I was too long, so I just cut it. And this is the second part of the talk. And then it was very funny that I was following also the methods of Herb. And I arrived to something like, just like he did. He used these infinitesimal methods to predict some behavior of curves and some threefold. And I got the same ingredients in this relative situation, in the open situation. So I just made some kind of conjectures that I'm using his name. I hope he doesn't mind. And then the miraculous thing about this relative case, about this Fano case, is that they can be completely solved. So his conjectures have been open for a very long time, and I put it on archive, and 3 days after that, some guy wrote me, I can solve them completely using my techniques. A student of Harris. Okay, I was very happy with that. And that's going to be the last part of the talk. At the end, I'm going to tell you some future directions and announce some conference that we have at CIMAT. I hope you like it. Okay, so let me start. We tried to formalize infinitesimal variation of mixed Hodge structure. I won't give the definition here. Just, and we work in the most simplest case. So we consider X to be smooth projective and Y a smooth divisor, just like that. And we studied variation. So it's pretty much la collider Spencer, like in the previous talk. So we were studying this shift, the logarithmic tangent shift. We can define it as a kernel of these maps, but intuitively the maps are those vector fields that preserve Y, right? So we are studying the formations of pairs X, but you can also modify the convex structure of Y. And so then, as I was telling you, we were inspired by Friedman, and we tried to do on threefolds. So we restricted to threefolds for most of the paper, or at the end of the paper, and we studied the mixed Hodge structure of this type of things. This is X like here, Y is now an anti-canonical K3 surface. I didn't write it, I think, but this was a K3 surface. So we could associate a cubic form on this group, H21 of X, using the derivative of the field map. And this is similar to the Calabi-Yau, classic Calabi-Yau situation. And this, you can also associate a cubic form in the Calabi-Yau setting, sometimes called Yukawa-Griffiths cubic. And we also got something similar here. Very strange. It is related to mirror symmetry in the classical case, counting curves, or at least Gromov-Witten. And this was at the back of my mind, like there should be something counting curves in this open situation. We couldn't do much about this, But using this cubic, we proved something that we call a generic Torelli theorem. So we could recover the pair using the mixed Hodge structure, but for generic pairs. So this was the first paper using infinitesimal methods. And now this H21 keep appearing and appearing. And then Philip asked, this looks like the intermediate Jacobian or the tangent space to the intermediate Jacobian. Is there some relation with, let's say, lines or curves inside X? So let us consider X to be a smooth finite threefold and Y a smooth K3. So we can consider the parameter space of curves of some degree. Let's call it C and fix a degree. So the main example I will have in mind, or you can have in mind, is you can think of X to be the cubic threefold and Z to be the final surface of lines. Okay, so the question is, how does this interact with the pair that we are having? So we have X and we have Y. Y is the K3. So we have something called the Abel-Jacobi map. We don't really need the definition. We need the differential. So in the previous talk, Javier was talking about the differential of some maps. We are also thinking here in the differential of this thing. So what is the tangent space of this set here? So this is simply the normal H0 of the normal bundle of the curve. So you have one curve of degree D inside X. You want to compute the deformations of it inside X. Okay, so this is going to be the tangent space of this set. And then the interesting thing is that we have H21 that was appearing before here in this differential of this map. So we have a theorem also in this. This is a second paper with Green and Griffiths. It has 2 points. So let me go to the first part. The first part is we keep X fixed and we see what happens to the image of this set. And the second part is we deform X. Let us go to the first part. We will assume for simplicity that the intersections are transverse. So now it depends on the degree you have in how many points you will intersect this boundary Y, this K3 surface. So let's think in the simplest case, you have a line, and on the cubic threefold, Y is given by cutting X with a degree 2 hypersurface. So this line, this red line, is going to intersect Y on 2 points. So actually, you can define a map from Z to Y to the power D just by sending where this curve intersects the Y. Okay, it's not complicated, but Y, the symmetric power of D, you have a hyperscalar structure, and induced by the symplectic form of the K3. So the first result here, it was actually, we found that it was known after that, is that the image of this parameter space inside the symmetric product is a Lagrangian submanifold of maximal dimension. So you map this set inside Y to the D by this construction that I just gave you, by sending the points of intersection, let's say in the transverse equation. And then you can find that this is a Lagrangian in the image is Lagrangian. Okay, so this was the first part. We keep everything fixed, and now we want to move. We want to deform X, but if we want to do something like this, we need to keep fixed the complex structure of Y. We cannot deform Y because this map will be moving. So I will introduce a second shift that is Tx minus Y. This simply means the shift of vector fields that are vanishing this time on Y. So the first one I introduced before, it was logarithmic. You can move the complex structure of Y, but this now you are keeping the same structure on Y, okay? And this fits into some exact sequence, just like this. And now, a funny situation is that in this log Calabi-Yau threefold is that we have an isomorphism. So Y is going to be on minus K of X. Using some contraction here, you have an isomorphism like this. And if you take cohomology, you end up in an isomorphism of H1. So in one side of the equations, you have a deformation problem, and on the other side, you have something Hodge theoretic. So this is imitating, or we're obtaining something similar in the Calabi-Yau situation. In the Calabi-Yau situation, you can control first order deformation by Hodge theorem. This was very much used by Hertz a long time ago, and this is what we want to use and generalize in the next part of the talk. Okay. So let us come back to the picture. I was telling you that this is for X fixed, and now we want to see what happens if we move X, but the deformations are keeping Y fixed. So this is going to define us two maps. One is just by taking the differential of where the line or the curve intersects Y. This is nothing fancy. The second one is a little bit more complicated. We can have a mapping to the normal bundle of the image of Z, and this is going to use the universal family of deformation keeping fixed Y. Okay. This is more complicated. I don't want to enter into details here. What the result says is that you can compute the differential of the Abel-Jacobi map using the symplectic pairing of the hyperkähler variety Y to the power D. Okay, so we are relating Hodge theory and symplectic information on Y and deformation. So this is very impressive. And
where are you? You are talking and I cannot relate it.
Yeah, sorry.
So what are you discussing? Which statement are you discussing now?
So this one. So let me read it if you want. So the symplectic pairing, this is on the Y to the D, the symmetric power of Y, links Hodge theory and the geometric maps, two maps that I have here. One map is given by the differential of this map. This is F. I'm taking the differential of this. This is given in one map. The other map is given by using the universal deformation associated to this problem. Okay, and now I have to take one element here. I have to take the other element here, and I will map it. One pairing is this one, just using the duality, and the other pairing is using the symplectic pairing that I have. And the result here is that these two coincide.
Size the symplectic pairing?
Say that again?
Size the symplectic.
Yeah. Size the symplectic pairing and induced by the form on the H reserve. Okay. Or yeah, I'm going probably too fast in this one. This was supposed to be the motivation only, but it's not ready yet. So I don't want to say about the proof. We can discuss it later. Okay, so I have a picture here, just what's happening in this second part of the theorem. So we are looking now. This should be some open bold B inside H1 of Tx minus Y. And instead of having the universal family of deformation of X keeping Y fixed, we are looking at the relative, let's call it final surface, if we think in the cubic threefold case. So each vertical red line is parameterizing the lines inside the deformation of X, and then we can map to the fixed Y to the power D that we have. And we have something like this. Okay, so let me just questions. So morally, what is happening is if you deform X keeping Y fixed, you map to the normal bundle of this image that we knew that it was Lagrangian. Okay. I mean, this is not the main part of the talk, right? Just the motivation that we were studying log Calabi-Yau threefolds. We were studying curves inside this log Calabi-Yau threefolds. And actually the main one ingredient for the proof of this is using some duality that goes as follows. So if you take a smooth curve there, so you can take the normal bundle. I'm gonna sketch the proof of this later. But you have a duality between the normal bundle of the curve twisted by y, and you will have a duality between H0 and H1. So in the Calabi-Yau situation for threefolds, this is log Calabi-Yau threefold as previously. And if you are in the Calabi-Yau setting, you have something that I call a perfect duality. So you have a duality between H0 and H1. So one of them is controlling the deformation, as we saw in the Javier's talk, and the other one is controlling obstructions. So here we don't have the exact same thing inside the same group. So I was asking, can we modify a little bit our construction to obtain something that really looks more like this, that we really have the same thing inside here? So the answer is yes, but we don't have to work on the log Calabi-Yau world. We have to work on something that I call the cube log Calabi-Yau setting, or more precisely, the 1/2 log Calabi-Yau setting. And actually here we are working with the Abel-Jacobi map for X. But if we
Why
really
don't you dualize N?
I mean, I'm going to give the proof after that. But
this is correct as it is without dualizing one of the N.
I mean, yeah, this is correct. So you should dualize it and tensor with K of C, right? So then you have some formula for K of C, and this will. I mean, it's really easy. Just you do this determinant of C of X. And this is trivial in this case, and the dual with this would cancel and would give you. So this was the question yesterday, right? Okay. So so let me introduce infinitesimal log Abel-Jacobi maps. So what are the idea of this? So the idea is that I want something that looks like the differential, but it should mix the information between X and Y. So before, the differential of the Abel-Jacobi only looked at X. Here I really want something that looks at both parts. So now, just for simplicity of the notation, let me do the case X has dimension 3 and C is a smooth curve. This works in more generality. And we have another exact sequence. So now we can restrict the vector field expansion to Y, we restrict it to C. So we can have two deformations of C. We can see the deformations of C that are inside X, or we can see the deformations of C that move with the deformation of the pairs. So you remember this sheet was controlling the deformations of the pair. So we can ask which one stay inside X and which one move with this kind of deformations. So we have something like this. Let me dualize to get forms. So I have the dual, the normal bundle. I have logarithmic forms. Let me just keep it like that. So we can tensor these forms with itself in following Griffiths to define the differential of the Abel-Jacobi. We can define a map of this sheet to this product. It's very easy. You just have to take one tangent vector to C and another one normal. We use this exact sequence. We can leave one here, and we can define a pairing just like this. So we obtain a map as projection like this, and we just take the homology. This resembles very much the block construction also of the semi-regularity map. It's doing something like this. It just takes a different kind of cohomology in the next step. So in the next step, we take H1 to this exact sequence, and we obtain something like this. We can use duality on the curve C, and if you look, this looks pretty much like the dual of differential of the Abel-Jacobi. So before I had something differential of the Abel-Jacobi, this was from the H0 of the normal bundle of the curve to H1 omega x2 dual. And here I'm doing something, but now I'm taking into account y. So if you dualize this map, this one is going from H0, but now I'm twisting the normal bundle. I'm considering the formations of C that keeps the point with y fixed. I think I have a picture in the next slide. Yeah. So I'm considering the formations of C, but I'm fixing the intersection with y, and I'm defining something that looks Hodge theoretically that could be called like the differential of some relative Abel-Jacobi map. Okay. So again, this can be done in much more generality. Just I'm presenting to you the three-dimensional case for my purposes, but I wrote it on more generality. Questions here? Okay. So now let me go to Q log Calabi-Yau pairs. We can go to any dimension here. It's not that complicated. So you let X be a smooth projective of dimension n, and Y is still a smooth divisor. So I will call the pair a smooth Q log Calabi-Yau threefold. Oh, sorry, Q log Calabi-Yau pair if there is an integer m such that we have this this equation here. So in the log Calabi-Yau situation, you take m to be equal 1, but we can modify this definition a little bit. And in my mind, what I will always have again is x to be the cubic threefold. And y in this case, if I put m equal to 2, y is going to be a hyperplane section. So it's going to be a cubic surface, and I want to relate. I want to apply my construction that I did before the relative Abel-Jacobi to this. So now we have a bunch of deformation problems. You can consider the deformation of x. You can consider the deformation of x that keep y. You can consider the deformation of x that keeps that vanishes on y allocs with some multiplicity, and a lot of twists of this. And every one of these is going to define an Abel-Jacobi type map. I don't want to enter into details with this. And you can also study the unobstructedness of these problems. And some of them are very easy just by using vanishing theorems and long exact sequence. Let me know going into details for this. So now, again, I want to consider curves inside let's go to threefold again. So now I want to consider the formations of anchored curves or relative curves if I want to think of them inside the open part. So I have two complexes. So one of them is controlling the deformation of the pairs X and C. This is pretty much the setting of pair in this Clemens conjecture like he did. And I want to twist. I want to do another complex, but considering the deformations of the pairs. And actually, I'm going to twist this one by O of minus y. So something very nice that we have in the Calabi-Yau situation, in the threefolds Calabi-Yau situation, is that deformations and Hodge theory are very nicely linked. So we also have this in this pair situation. So you have some sequences. So this is the one that I was writing here. I'm just twisting it. And using the volume form or using the Q log Calabi-Yau definition, you will have, let's call a volume form with higher order pole that will induce isomorphisms between these things. I don't want to enter into the precise formulas of this. The important thing is that when you take H1 or when you go into cohomology of this will give you the infinitesimal Abel-Jacobi maps for pairs that I was defining in the previous section. So you have a commutative diagram here. One is controlling deformations, and the other one is looking like Hodge theory. So when you go to cohomology, what this is saying is that one is controlling some deformation problem, and the other is giving you the relative Abel-Jacobi map. So this is linking. This is the one I want to say. So this is linking Hodge theory with deformation. This is precisely, again, the setting on the Calabi-Yau threefold. Let me ask for questions here. So the formula looks probably really bad, and I don't want to. So once again, what I want you to take is that you have some deformation problem on one side, you have Hodge theory on the other side, and if you are in this Q-log Calabi-Yau threefold setting, you have a bridge between them. That's all I want to say in this setting. So I was talking about these dualities between the normal bundles H0 and H1, and so we have general formulas to compute this kind of dualities. And the magic trick here is that if you set M equal to 2, you will obtain the duality that I was searching, that I was telling you before. So if you are in this setting, you obtain a duality between H and C of X minus Y and H1 and C of X minus Y. So what is this saying? This is saying that if you want to study the deformations of the curves that are fixed in some way to Y, deformations are dual to obstructions of this kind. So this is defining you some enumerative problem, and this is saying that you have vertical dimension 0 in some way, so you can count things. You can expect to count things. And this is where we are heading. So let me continue. So once again, this is the duality I was searching when we started the talk. I was telling you that with Griffiths and Ring, we were studying this equation, but we didn't have the perfect duality that I was expecting. But in this case, in this one-half log Calabi-Yau, we do have it. And the proof is really what I told here. So you use set duality at first, then you use the adjunction formula. And the magic step, the important step here is that the normal bundle is of rank 2. So you have a formula for rank 2 bundles here. So you have the determinant on one side, you twist it with the dual, and you come back to N. So this was Eyal's question that why don't put the dual here? It's precisely because of this equation. So the same works in this twisted setting. I'm just twisting by minus Y, and I obtain the duality that I wanted. I'm going to stop for a minute here, just for those who want to see the details. Okay, so now I have all the ingredients to do the same as Eric did a long time ago. So he had the same situation in the Calabi-Yau threefolds. He had the differential of the Abel-Jacobi map. He had this equation. So the geometric idea is if you go to some special Calabi-Yau threefold and it has a lot of rational curves, you can deform X and see which curves will go with the deformation of X. So now we have the same ingredient here. I think I have a picture. Yeah. So let us think in the Fermat cubic threefold on the picture. in that. You can have a cone of rational curves passing through some special point. So you can deform the Fermat cubic threefold, and you can ask which lines will go through this deformation. So the main ingredient that there, from what I understand, he used the Abel-Jacobi map, and he knows more or less what the kernel of the Abel-Jacobi should be and how should this behave. And so he asked, if you have the differential of the Abel-Jacobi, now I have this one in this relative situation, is this injective? Why? You have some reasons. If the answer is yes, then you have some boundary map that is controlling deformation problems, and then some cohomology group should vanish, and this will tell you the information about the structure of curves. So let me now go to the conjectures. So if you are in the setting that I wrote, X is a smooth threefold, Y is in 1/2 minus K of X, what I call the 1/2 log Calabi-Yau threefold pair. Let us consider C to be a general smooth rational curve of degree D. So very similar to the quintic situation. You fix the degree, you have a rational curve, and you want to fix the intersection. So all along the talk, I have said that I'm fixing this minus Y. This is vanishing along the Y. So I'm fixing the intersection points. And so this conjecture, the analogous conjecture of F, have 2 points. So the first one is, if you fix the locus where this degree D rational curves will intersect Y, there should be only a finite number of them. But we are fixing. And the second one is, if you twist the normal bundle by minus Y, the normal bundle can be described to be O minus 1 plus O minus 1, exactly the same as in Ert's equation for the quintic. So again, I'm not saying these are the conjectures of Ert. I'm just saying I use the same path, the analogous methods to deduce some conjecture. Okay, so I try to compute this differential of the Abel-Jacobi in this relative situation in some examples, in the Fermat cubic threefold examples. It was injective, it looked good. I tried to do some computation by hand, computing lines, conics, but everything looked good. But then somebody came and say, we can use Gromov-Witten invariants and solve all of them completely if X is a final threefold. Okay, so this was very impressive for me, and of course the techniques that I don't understand them very well, but I will try to give you a sketch of the proof. So now the conjectures that I put was for 1/2 log Calabi-Yau threefolds. So here we have to restrict to X to be final. I'm not sure how far is that from the general equation, maybe the expert know, but so the theorem is as follows. Let us consider a final threefold of index 2. And the degrees in these numbers. So X, Y, and Z to be general. Y was the hyperplane section. C the rational curve of degree D. So there are finitely remaining answer curves with the same degree, and they are balanced. So even though the methods are from Gromov-Witten theory, the proof is really geometric. So I want to give you the proof of this, or at least a sketch of the proof. So Zachariuk proceeds as follows. You have a threefold. Let us consider a Lefschetz pencil of hyperplanes. So you have also Y. Let us ask that this Y0 is the Y we started with. So now, the base locus of this hyperplane section is going to be an elliptic curve if you ask for this pencil to be general enough. And then we had some points that we were fixing. So we had, you fix some points on Y, and he says, let us specialize these points to the base locus. Let's see what happens. So in the original conjecture, I was telling you, you have X, you have Y, you fix one rational curve that intersects Y on this set, and you fix this. But he says, no, let us specialize more these points to the elliptic curve. So, and let's see what happens. We consider the blow up along this elliptic curve just to have this a good family. And so the first question is, can a rational curve C pass through these D points on E while remaining transverse to the fibers of the pencil? I mean, you have now a pencil, and you can ask, are these rational curves passing through these points on one fiber, or can they be transverse? And the answer is this: they cannot be transverse. And he used something like the Bezout theorem, basically saying that if a curve vanishes in more points that generically allowed, they should be forced to be on one surface of this pencil. So the conclusion is that the curves cannot be transferred. They must lie completely inside one of the textile surfaces of this pencil. And now, how many curves can we have on this vertical hyperplane section? So can they be infinitely many? No, we only have finitely many. So what is the argument? The argument is, if there were infinitely many curves passing through these D points that we specialize to E, by properness, they will cover the whole surface. So this would induce a dominant rational map from a rational curve to the elliptic curve E, but there are no non-constant maps from P1 to an elliptic curve, so this is not possible. We should have only finitely many. And now, in how many lines, in how many surfaces can one line be? So can there be infinitely many? So the answer is no. There are only finitely many surfaces where such a line can or a curve can live. And the argument is using Picard groups. So the Picard of the fiber is discrete, and the Picard of the elliptic curve is continuous. So he had some conditions using genericity, and so he concludes that only finitely many surfaces contain this type of lines. And so he established that there are only finitely many curves using this. You force the points to lie inside an elliptic curve. You see how many surfaces can there be containing such type of curves. You see that there are only finitely many. You sum over all the surfaces containing this, and that's it. Then you have to argue that this specialization process didn't break the actual number. This is obviously the hard part. And that's it. You can finish the argument with this. And moreover, once you trap the curve inside one surface, he can describe the normal bundle very easily because it's inside some surface. And then we need hard theorem. So he has found one special curve. He needs to generalize that to the general setting. It's also an argument that they are used in this EHS paper. So he constructed one curve very special, and then he moved it to in moduli. So we need to consider the Conjecture moduli space of rational curves. So then we need to use results of Koskun-Stark or Lehmann-Tanimoto telling you about the structure of these rational curves. So this is interesting. This Lehmann and Tanimoto, they have some theory of distribution of rational curves. So it's pretty much what Professor Javier was talking at the end of his talk. So how these rational curves behave like rational points, how they distribute inside these threefolds of index 2, and these conjectures is coming to the same point, but from a different point. So basically, what they are saying is that these rational points or these rational curves are evenly distributed. So, I mean, if you're in the generic situation, when you pull back a point, happens what this relative Clemens conjecture tells you that is going to happen. So once you have this, you apply these theorems, you can use this specialization of Zaharyuk to the general situation, and you can conclude using the open, that this balance property of the normal bundle is an open conditions. So that's basically the idea of the proof. On the paper that we put on archive, we decided to write it in a more cryptic way. So we use relative Gromov-Witten invariance or something like that. It's not this argument. This argument is in a paper of Zaharyuk. In this thesis,
But did you say what the degree comes into play?
where the degree comes into play.
When you
here.
But those restrictions to be.
Say that again.
Your degree is restricted for this 2, 3, 4 times.
Oh, the degree of the del pezzo. Okay, so we have 2 degrees here. We have the degree of the threefold and the degree of the curves. Those are different things.
Yeah.
Okay. Yeah. So you want to see what's the importance of the degree here?
Just
so I think because he uses you want to use something that is very ample. The main scale of X is very ample. If not, you have some kernel in the anti-canonical map or something like that. You can break at some point. I don't think it's very important. I mean, the one missing there is, I guess, 1. But I think you can push his argument. Yeah, so this D is XD del pezzo. So you have also C. This is a rational curve of degree E. Let me call it E. I'm not sure. Probably I did. So yeah, it's probably my bad.
Okay.
So there are different things. So here I'm taking Z. In Z, I'm moving the E points to the E. So this one is not depending on D.
Yeah,
this is yeah. Okay, my bad. Yeah, this is my mistake. Okay. I'm sorry, very sorry for that. But there should be E, and it's independent of.
Okay.
And so it works for every E. It works for. I mean, this is fine.
No.
Here we have problems.
Now
it's my bad. Yeah. So if we compare with the law of Calabi-Yau situation, and also the Brad was here when so in the law of Calabi-Yau situation, I was telling you, you have the parameter space that I call Z, is basically this one, and you map to Y is going to be a anti-canonical K3. I was telling you the image is Lagrangian. So you have half the dimension. I call this F. So now here, the magic is that if you go to the 1/2 law Calabi-Yau setting, the dimension is the same. So you can, at least the expected dimension, that's the conservation moduli space, really the work of this Lehmann, Tanimoto, these guys, they show that the expected dimension is actually the dimension of this moduli, conservation moduli space. That's really important because it's telling you that when you take this map, if it's generic enough, the fibers is going to be only a finite number of them. And that's precisely the phenomenon that give us the possibility to solve that. In the quintic threefold case, you have a lot of branched coverings, and if you want to use Gromov-Witten, you have a lot of noise that keeps you from counting. And here a consequence of your result is that Gromov-Witten are enumerative, so we can use the properties to really count and to solve these conjectures questions. Okay, so let me give future directions for this. So I really think this Q log Calabi-Yau is behaving like Calabi-Yau. We just need to find the sense of it. Something that is missing is the volume form. So I tried to copy a lot of their arguments, and they break down because I don't have a volume form. So but actually I do have a volume form if I consider a double pole. But I think Hodge theory becomes complicated if you consider double poles or higher order poles. You have to use something called Chow groups with modulus or relative Chow groups with modulus, something that has been recently developed. I'm not sure if everyone is aware of this. And once we have this, once I expect to learn this, I want to apply it to the finite of relative normal functions, relative groups, blah, blah, blah. So another thing that can be done is we can study higher genus. I only did it for rational curves. The result that I talked about with Mark and with Philip, it was for any genus as long as it was a smooth and transverse. But I only did this for the for genus 0. This the duality between H0 and H1. This holds for every genus as long as C is smooth. And also that I don't know how to work is when we don't have transfer intersection. So if you want to really do relative Gromov-Witten invariant, you have to see what happens when 2 points collide, or when you have generations, when you have tangencies, and we don't know how to do this. I mean, even from the Hodge theoretic point of view, I don't know how to solve it. Probably we should use log Hodge theory, but I'm not really sure about this. And so something that I also have in mind is considering the birational geometry of this Q log Calabi-Yau pairs or even 1/2. So what do I mean by this? So there are a lot of viewpoints from these cluster algebras. And one of them is by considering birational transformations of log Calabi-Yau. So what happens if we ask the transformations to preserve this double pole volume form? So these are just vague ideas. I don't have any results in this direction anymore. This just serves to introduce the conference announcement. So we are organizing some conference in Guanajuato, in CIMAT, with the kind support of IMSA. So regulators, log geometry, and log Clemens Conjecture. If you are interested, if you want to come to Guanajuato, you are all invited. So we plan to study these things that I just put on the previous slide. We expect to have some mini courses. We are contacting the people, so you are most welcome if you want to come. So thank you very much.
So of course, modern science have a different way to talk about this, but let me talk in your language.
Who's that?
Modern science has a different way to talk about this, but so there is no way you study Sarkisov program because in the case of log Calabi-Yau, all of the Sarkisov links correspond to volume preserving transformations, and you won't have this.
Sure. Some generalization of some.
This finiteness and the theory of homology is going to be lost. Now, of course, you might use some relative Gromov-Witten and put some connection there, and so therefore that will give you some advantages. But I mean, in a situation like that, you have this sort of herb introduced 40 years ago, something which is called defect, and it's going to be all over the place. And you just need to bound it in some way. But that, at least from the works of Alessio and other people, it's not so simple.
Yeah, I mean, I tried to do some Python calculations, but so far, but I mean, it was for catching the attention and it worked. So happy with that. Any question?